We're starting something new today called systems of equations. As we often do, we're going to start with a little bit of vocabulary, starting with the definition of a system of equations. A system of equations is defined as two or more equations that share the same variables. Two or more equations with the same variables. Everything you do in Algebra 1, or in this Algebra 1 lab class, we will just have two equations. When you get to Algebra 2, you will have systems of equations that have 3 or possibly even 4 variables in there. A system of equations looks something like this. So we'll have two equations right on top of each other. Maybe the first one says y equals 4x minus 1. The second one says 2x plus 5y equals 20. So notice I've got two equations. They have the same variables, x and y. Often you will see a little curly bracket on the left side here that's showing that we are putting those two equations together in the same system. That is what a system of equations will look like. We will usually be asked to solve the system of equations. So let's talk about what the solution to the system looks like. The solution to a system of equations is the value of the variables that makes all of the equations true. The value of the variables that makes all equations true. So if we have a system of equations that has 8 equations in it, and we have found what we think might be a solution, and we're checking it, and it works in 7 of those equations, but then it makes the last, the 8th equation false, it is not a solution. It has to work in all of the equations that are given to be a solution. There are 3 different ways that you will learn to solve systems of equations. The first is by graphing. Solving a system of equations by graphing. That is what we will be focusing on today. You will also learn how to solve a system of equations by substitution. And finally, elimination. Solve a system of equations by graphing, substitution, and elimination. Again, we are going to focus on solving by graphing today. To solve a system of equations by graphing, remember we have 2 equations. So we are going to graph each line on the same coordinate plane. So we're going to make a coordinate plane, we're going to graph both of the lines. So maybe I graph my coordinate plane, I graph the first one, I find the y-intercept, and I find the slope, and I get the points on the graph, just like that. Those are all the points that are solutions to the first equation. And then I graph my second one, and I get something that looks like this. Those are all the points that make the second equation true. We are going to be looking for where the 2 lines cross. We want both of those equations to be true. They're both true at the intersection point. The solution is where the 2 lines intersect. The different types of solutions that we could possibly have, most often we just have that one solution. The 2 lines intersect each other at exactly 1 point. So I graph 2 lines, they cross each other once. I just have that one solution. I state what that solution is. It's also possible that my 2 lines, I graph the first line and it looks like that, and then I graph my second line and it never crosses the first line. I have parallel lines. Remember, that would happen if they have the same slope. If that's the case, there is no solution. We would graph the 2 lines, and then we would state that the graph, or that the system, has no solution. No solution will occur when the graphs of the equations are parallel, when they never cross each other. And then finally, it's possible that I graph my first line and it looks like that, and then I graph my second line and it lines up right on top of that first line. They wind up being the same line. When that's the case, those two lines, those two equations cross each other at all of the points on the line. There are an infinite number of solutions. We state infinitely many solutions. And the graphs of the equations are the same. So if we get the same graph for both equations, we state that there are infinitely many solutions. So let's try a couple of these. The first one, we are given y equals 2x minus 3 and y equals x minus 1. Y equals 2x minus 3 and y equals x minus 1. So again, we draw our coordinate plane, and we're going to graph both of these equations on the same coordinate plane. So y equals 2x minus 3 is in slope-intercept form. Slope-intercept form is y equals mx plus b. We will always graph the y-intercept first. Always graph the y-intercept first. So our y-intercept, our b, is -3. So starting at the origin, I'm going to -3 on my y-axis. I put a point. And then my slope, m, is 2. So from that y-intercept, I am going to go up 2 and right 1. 2 over 1. Rise over run. Up 2 over 1. Up 2 over 1. And we do want to fill up the entire graph. We started at -3 and we went to the right. Notice I could also go left 2 and down, I'm sorry, down 2 and left 1 will give me a point on that same line. And we've got a bunch of points we can draw our line in there. Y equals x minus 1. Y equals x minus 1 has a y-intercept of -1. And the slope is understood to be 1. We're going to go up 1 over 1, up 1 over 1. And remember, we're looking for where the lines cross. Once I have found where they cross, and graph a couple more points on that side. But I don't need to fill up necessarily the entire graph now. Once I've found that intersection point, we graph our line in there. And notice we do have one solution this time. These two graphs cross each other once. It is important to state what that solution is. X is 2, y is 1. Let's write it as an ordered pair. 2, 1. We put the x value first and then the y. We can verify that that is a solution to our system by plugging it into all of the points. I think that's what this says over here. Plug in the ordered pair to make sure it is a solution to both equations. So if I plug in 2 for x and 1 for y, this is going to say 1 equals 2 times 2 minus 3. 2 in for x, 1 in for y. 2 times 2 is 4. 4 minus 3 does indeed give me 1. It works in the first equation. It has to work in all of them. If I put in 2 for x here, it says 1y equals 2 minus 1. That's also true. Our solution is correct. Example 2. Example 2, we're given y equals x plus 5 and y equals -4x. Y equals x plus 5 and y equals -4x. Y equals x plus 5. Y-intercept is 5. Slope is 1. Rise over run. Those 2 points are great. We probably should get some more over here somewhere. Staying on that same line, so I went up 1, right 1. I could go down 1, left 1. Also has a positive slope. And again, I'm going to fill up the entire graph that's given, at least on the first one, and we can draw our line in there. And now we can graph our second line. Second line, y equals negative 4x. Y equals mx plus b. I don't have any plus b on there. That's the same thing as plus 0. Y-intercept is 0. Slope is negative 4. So we're going to go down 4 over 1. Notice if I keep going down 4 over 1, I'm not seeing where it's crossing over here. So that's why it's important to graph some points to the left of the y-axis. If I'm on this same line, I would want to go up 4, left 1. And not a very straight line on my part, especially right there. But we do see our intersection point. It's right here. We list our solution. X is negative 1, y is 4. Example 3, y equals negative 1/2 x plus 2. And 3x plus y equals negative 3. Y equals negative 1/2 x plus 2. And 3x plus y equals negative 3. Let's graph our lines. First one's slope is negative 1/2. Y-intercept is 2. Always graph the y-intercept first. Negative 1/2. Usually we'll see it written like this. Rise over run. Rise is negative 1. Run is 2. Down 1, right 2. Down 1, right 2. Can also go up 1 and left 2. This equation, our second one's not in slope-intercept form. That is point-slope. That's not point-slope form. That's standard form. X and y are on the same side of the equation. When that's the case, we can either find the x and the y-intercepts or change to slope-intercept form. I am going to change to slope-intercept form, and we can do that by subtracting 3x from both sides. I prefer to graph from slope-intercept form, so I am going to change to slope-intercept form. Negative 3 minus 3x. Let's put the x first. Negative 3x and then minus 3. So y-intercept is negative 3. Slope is negative 3. So we're going to go down 3 over 1. And again, this is 1. I'm not seeing where it's intersecting over here, so we can also go up 3, left 1. That's on that same line. Up 3, left 1. Up 3, left 1. Notice down 3, right 1. That's negative 3. Up 3, left 1. Positive divided by negative is also negative 3. And we have our intersection point right here. It is at negative 2, 3. We're going to stop right there. We will continue next time. We will take a look at some that have either no solution or infinitely many solutions.